Okay, so we start with the actual science. And the actual science is with lowly principal component analysis. It's and it's a bit of a statement that I'm starting the course with this. Yes, I'll tell you later, okay? So principal component analysis, it is a technique for dimension reduction and also for visualization. And you know, when I can start talking about machine learning, I could have chosen any topic, but I chose this one because I really want to emphasize that it's so important to visualize your data whenever you're working with data. Because usually, no matter whether it comes from simulations or from measurements or something, usually there's something wrong with it. And part of the problem is finding out what is wrong and how to deal with it. But first, you need to know that something is wrong or that there is some surprising structure in your data. And some of the nonlinear methods, which we will see on Thursday this week, are even better at uncovering such surprising structure. But it is really important, and this is why I'm repeating it over and over, really important to look at your data. And this is why I'm starting with principal component analysis. And now I do that even though it's not even mentioned in the book by Bishop, because it's not Bayesian, but it's extremely useful. And the plot I show here, it comes from, well, today's Tuesday. So this plot started my week. Each Monday morning we have a stand-up and we say, what have I been doing last week? What is my plan for this week? And then Christoph Gehrig showed this plot. And, you know, I mean, we're doing pretty complicated science and pretty complicated machine learning, and yet we use principal component analysis. Yeah, it's a super important and useful tool. And well, what we see here is these are systems that live in a 400-dimensional space, and there is a good scientific reason why we perturb these systems randomly, and then we try and find some optimum. And here you see those trajectories where in 400-dimensional space these systems move, and you can see how they converge to this point. And highlighted here in color is, in addition, how big was the gradient norm at each of these steps. We can see that the point where they do converge is different from the point where they should converge. Yeah? So this is the ground truth solution. This is where they do converge. But you know, broadly, you know, this distribution and are things moving, you know, out first or not, and so on. Imagine not having this figure, but imagine instead having a table. Yeah, the table would have, let's say, 400 rows for the 400 dimensions, and then I don't know how many points these are. If these are 200 points, you would have a table with 400 times 200 numbers, and unless you know you're some alien life form, it's just very difficult to make sense of such tables of numbers. And hence, it is really important to look at your data. Good. And so today, let's look at this principal component analysis in detail. And here, I'm fighting the decay of Western civilization because it's principal component analysis, okay? So first exam question in the upcoming written exam, how do you spell principal component analysis, okay? and if you spell it not like so, but if you spell it with an LE, You've already, you're already out. Okay, so in English, there is the principle. The principle is, how do you describe a principle? That's in German, das Prinzip. But this is principal, in which in German is main, Haupt. Okay, so here we're talking principal component analysis. And I'm mentioning it because somehow more and more people are copying from people who wrote it wrongly previously. And then in the end, society collapses. So principal component analysis. Okay, so what it does is it projects our data to the best linear subspace. And I think linear is clear, but what do I mean by best? I will explain in a moment. And why the motivation is dimension reduction, which is sometimes even beneficial, because sometimes this dimension reduction gets rid mainly of noise dimensions and then makes actually the problem better posed. You can look at it as a form of lossy compression, and you can use it for visualization. It's an important baseline visualization method, even though there are better ones. And the justification of why it's okay to do that in the first place is that usually there is something called the intrinsic dimensionality of data, and this intrinsic dimensionality normally is much lower than the nominal dimensionality. So, for example, if you look at, let's say, pictures of human faces, if you have a picture of a human face and this has 1,000,000 pixels, then the nominal dimensionality of your data is 10 to the 6. Yeah, we have 1,000,000 pixels, that's 1,000,000 numbers. So I can say each picture of a face is 1 point in a 1,000,000 dimensional space. But if you then look at the kinds of faces that humans actually have, it can be male, female, anything in between. It can be, with more or less facial hair. It can be with more or less hair on top. It can be different colors of hair and skin and all that. Different shapes of nose, mouth, eyes, etc. But when you enumerate all these different things, maybe you come to 20 dimensions or 50, but let's say for the sake of argument, even 100 dimensions. Yeah? But then this is 100 numbers, and that's much less than the 1,000,000 numbers that you have in all the pixels. And that's a very, very typical finding if you look at real data, that this intrinsic dimensionality is less than the nominal dimensionality. And we will at the end of today, talk about the principal component analysis way of measuring how much information is in which dimension. And you get plots like these that tell you for the different dimensions how much variance they explain. And normally you observe, this very, this exponential decrease with dimensionality. So if you want to fully reconstruct an image up to the last noisy pixel, well, then you need, then you might need the 1,000,000 numbers. But to get a decent approximation, it's often enough to just use the first, depending on the problem, 2 or 3 or maybe 100 principal components. Okay. So when is this method applicable in the first place? Or what are the assumptions? One assumption is that your data has at least interval scale. I will explain what I mean by that. In measurement theory, there are different kind of scales. There is as the least informative is a nominal or categorical scale. And a nominal scale, you know, that could be things like whatever, a bear, the animal bear, and I don't know, let's say apple. These are two different you know, entities, and you cannot say that a bear is more than an apple or is less than an apple. You could say that one weighs more than the other, but you know, there's just no way to directly compare. Then there is an ordinal scale where we could say we have, for example, little and much. Now, we don't know how much more much is than little, but there is a natural ordering, hence ordinal. Then there is the interval scale, where distances between numbers are meaningful. And so I'm writing here differences are meaningful. And the most informative scale is the ratio scale. In the ratio scale, you have meaningful differences, and you also have an absolute zero. Okay, so we have these different scales on which entities can be defined. So in classification problems, we usually have categories. And these categories usually live on a nominal scale. In a regression problem, we might have data that lives on the interval scale. And here we assume that data lives on the interval scale. So principal component analysis is immediately applicable only when you have numbers whose differences are meaningful, but not when you have a table which has entries like bear and apple. Okay. That's one assumption, and the other assumption is that the scaling of the axis is meaningful. In particular, if I change the units on one of the axes from hartree to millihartree or from gram to kilogram, I of course amplify my numbers by a factor of 1,000. And in principal component analysis, we assume that the axes are commensurable. Yeah? So we basically interpret distances between points as Euclidean distances, and that is only meaningful if the scaling of the axes is meaningful. Okay. Then what we need for PCA, let's say the input is a collection of observations, and usually we collect these here in a matrix. I'm usually just using capital letters for matrices and small letters for vectors. And now here, two different conventions are used in the literature. Many textbooks do it the other way around. I happen to make this choice, where P here is the number of features or the number of measurements that characterize an instance, and N is the number of examples or number of instances. And what you should not put into PCA, you should not usually put the outcomes in there. Yeah, so in classification or regression, we often say that we have features X and then we have outcomes Y. And sometimes they are collated into a single matrix. So then your matrix has not P by N columns, but P times 1 plus N columns. But then you use the outcome in the visualization, which normally you don't want. Normally you simply want to show what are, how is your data characterized in feature space. All right, and it is useful to subtract the mean, because otherwise your principal components are going to be dominated by how far are you from the origin, and not what's the intrinsic structure of your data. And the mean, we can write in terms of components. So this was the features, this was the instances. So I'm first index is for the rows, second index is for the columns. Here I'm summing over the instances. And well, this is the mean vector. And if we want to express this in matrix notation, we can say that this is 1 over n. And now I'm multiplying from the right with a vector of ones. So this is p times n. And this vector of ones here is now n times 1. Okay, and this is the same thing. And we now want to center the data. So I can say that x centered is x minus, and now we take this mean. And now we replicate it many times. So let's look at the dimensions. This is p times n. This here is n times 1. So the whole thing is p times 1. And this here is 1 times n. And then overall, I get something which has the right dimensions, p by n. So I have two matrices of the same shape, and I can subtract one from the other. And because x appears twice, I can now multiply it out. And I have here the n-dimensional identity matrix. And this entire thing is also called a centering matrix. Which sometimes gets its own letter. I could say this is an n-dimensional centering matrix here. Okay, so we have subtracted the mean. And from now on, I will assume that the mean has indeed been subtracted. And now I'm going to plot the typical PCA picture. Feature 1, feature 2. And I now have observations, and I now assume that the mean has already been subtracted. So the center of mass of these points lies in the origin. And now I can discuss the merit of a trial solution. So for example, as a trial solution, I could use this one here. And in PCA, we now ask for each point, how far is it from this trial solution? We ask for this residual here. Or we ask for the sum of squares of those residuals. Okay, and well, I'm too lazy now to draw all points, but you see that if I pretend that each of these here, if I say sum of squares of residuals, that sounds like, you know, harmonic spring. So if you imagine that I put a harmonic spring here for each of these, and if I relax my system, you can see that there's a net torque. It's going to pull it down on this side, it's going to pull it up on that side, and my final solution will probably look something like so. Okay, now the residuals here are symmetric. There's no net torque on the system. This plot looks very similar to the plots of linear regression that you've seen in high school. But I hope you spot the difference. What's different from linear regression? Okay, and we now parameterize this thing with a vector W that points in the direction of this first principal component. So that's a trial solution. That here would be the final solution. And there are now different ways to optimize this. One way would really be to do gradient descent, but then we still need to find the projection of each observation on our trial solution. And this is what we're going to do now. So let's say this orange residual here I can obtain it. I will make this simplifying assumption that W is normalized. So W transpose W is 1. And now I need to ask where does this point here lie? To find this point, I can take an observation xi, and I can project it onto my vector W. And this is now a scalar, and this scalar I need to multiply with W as a whole. And if I want, I can also write it the other way around. I can say this is W transpose xi times W. That's a scalar, and this is my vector. Yes? A little bit bigger. I will try. Thanks. So I was asking this point here, and I'm just writing the same thing bigger. Okay, that's the coordinate of this point. And now we will subtract, and this is my original point xi here. And now I will subtract the 2 and take the squared. Yeah, so I can say that this was xi minus W transpose xi W. Okay, this is now the residual squared. Is this formula here. And if I now want to write it, and well, now what I could do is I could sum this over all points I, or I can try and write it in matrix notation again. And this is why I used this. So this here is P times 1. And now I'm using here this P times N matrix. Okay, and from this matrix, we want to take all elements squared. This thing here is called a Frobenius norm. I'll write it down in a moment. So if we have any matrix A, and we want to take the Frobenius norm squared, it just means we take all elements and square them and sum them up. Or I can write it in terms of the trace. And this is what we are doing now. So what we have here is this sum of squared residuals. And I now want to find the this parameter or this direction W, which minimizes that sum of squared residuals. Yeah. So I can say, for example, I'm looking for a W which should be normalized of the sum of squared residuals. This was the formula, and I now use the trace to express this squared Frobenius norm. So I'm transposing what's written in there. Check dimensions here. This is n by p, and this is p by 1 by p, and the whole thing is n by p. This is fine, as is this one here. Good. Yeah. These things here, yeah, so these are not indices, it's just my checking the dimensions. But still, I will try. Thank you. Yeah, keep reminding me. It's reinforcement learning. And you win in the end. Okay. And we multiply this out. We will find that this term here we have twice actually. I had a mistake here. This is WW transpose. Okay. And now this thing, W transpose was 1 by p, and this was p by 1. So this thing here is a scalar. And we demanded that W transpose W is 1. So in other words, this thing is just the number 1. And then I recognize that this term is of the same kind as that one, and I can subtract them from each other. Okay. So this is still our optimization problem, but this part here is independent of W. So if we want to minimize with respect to W, I can simply ignore the term on the left-hand side. And what's left is that I want to make this as small as possible, or because we have a minus there, equivalently, I can say I want to make this trace here as large as possible. And I'm using cyclic permutation under the trace here to write this as W transpose X, X transpose W. And another way to write it is to take this normalization constraint in the denominator and the entire thing is a scalar, so I can just omit the trace here, because the numerator is a scalar anyways. Okay, and now we have this beautiful problem that you have seen many times. The Rayleigh-Ritz ratio. And this is a quadratic form in the numerator. So if we plot the numerator, this will look, if I plot equicontour lines of the numerator, it will look something like so. So a set of nested ellipses. But then I have my constraint. I have this constraint that W transpose W should be 1. So this is my constraint. And now my drawing here is not perfectly symmetrical, but we're trying to maximize it. Yeah, so those equicontour lines tell us that we have a parabola coming out of the blackboard here, pointing towards you. And on this parabola, we have this ring. And now we're looking for the maximum value of this parabola along the ring. And those maximum values are somewhere here and somewhere there. And forgive my painting or my sketch, which is not perfectly symmetrical, but it looks something like so. So in other words, these 2 points here are the solutions to my maximization problem. And the Rayleigh-Ritz theorem tells us that this maximization we can obtain by solving this eigenvalue problem here for the largest eigenvalue. So the solution, or the Rayleigh-Ritz theorem, tells us that solution is given by the eigenvector to the largest eigenvalue of x transpose w equals lambda w. So this is the eigenvalue problem that I need to solve. All right, and a comment here about the nature of this optimization problem, because this is a unicorn of an optimization problem. It's one of a very rare kind of optimization problem. So we have here, this is a convex objective, and I will say another time I give recall the formal definition of what convex means. This here is a non-convex constraint. So that means overall, convex objective is good, but non-convex constraints means that overall, this here is a non-convex optimization problem. And normally when you hear non-convex optimization problem, you think local minima, you think no guarantee of finding the optimum and so on. You think no closed form solution. But in this whole world, okay, so there's this world of optimization problems. It's the world of optimization problems. Most of them are non-convex. A small subset of these is convex. This is the island of happiness. Yeah? This is the convex optimization problems. Those are the ones which you want to have, which are easy to solve. And what we have here, this Rayleigh-Ritz ratio, this lives on the non-convex side, but right on the border, you know, it's almost on the shore of the island of convex happiness. Because here we have a closed form solution, and well, actually, we get out two equivalent solutions. They're equally good. My solution is only defined up to the sign, but still, I have a closed form solution. So this is as good as it gets in the world of non-convex optimization problems. All right. And now I went a bit over time on my first lecture, and I have not given you the formal summary yet. So this gives us the direction of the first principal component in a closed form. And then we can iteratively find the next ones. And then we can project onto the subspace and make pretty plots and so on. And I have a question for you for my preparation for next time. Are you familiar with robust estimators of location? So everybody knows the median, I guess. Yes, median, yes. But do you know sort of the theory behind or what other estimators there are? Robust estimators, robust statistics? Okay, good. Then we'll do a little bit of that next time. Good. There was a question from you. So the exercise sheets and so on. You will get the first exercise sheet on Monday next week. And the information is all in the Übungsgruppensystem. And the Übungsgruppen itself, Python tutorials, Wednesday, Thursday, Friday. Have a good week. See you on Thursday.